Okay, so we left off our discussion of how the universe got to be the way it is today with the time point our solar system began to form. We're going to pick up there this week and continue on through the formation of our solar system, and specifically the formation and history of the Earth. By the end of this lesson, you should have the information that you need to model current theories of how our solar system and our planet formed. So, right off the bat, I want to remind you that science is evidence based. So, just like with our discussion of the Big Bang and the early universe, we have evidence that whatever theory we come up with has to be able to explain. So, what you're seeing on this slide is a list of some things that we have observed about solar systems, both our own solar system and others that we can see. The first thing we've noticed is that solar systems tend to have disk shapes. They're shaped kind of like a dinner plate. And the orbits of planets within those solar systems all tend to be in the same flat plane. Meaning, if you had a solar system on that dinner plate, all of the planets would go in circles on the plate. None of them would be going through the plate. With a couple of exceptions, in our solar system specifically, we're talking about Venus and Uranus. All of the planets in a solar system tend to go around their orbits in the same direction. And that direction is the same direction as the rotation of the star at the center of that solar system. We've observed two major types of planets. Closer to the sun, we tend to observe rocky planets, which we call terrestrial planets. And farther away, they tend to be mostly made up of gas with liquid or icy cores, which we call Jovian planets. Overall, we observe that there is a certain amount of debris in space, by which we mean things like meteorites, asteroids, comets, stuff like that. And we've noticed that the farther away from a sun a planet is, the more stuff it tends to have in orbit around it. And finally, we've taken data and measurements. You know some of the ways that we do this from the last couple of weeks of lessons. And it turns out that all of the stuff that we've measured in our solar system is around the same age, about 4.6 billion years old. So, our explanation for all of this data starts with what we call the nebular hypothesis. And the basic overview of it looks like this. So, we already know that the early universe was filled with atoms because as it cooled, energy condensed into matter. And we know that as soon as we had atoms, we started to see gravity pulling those atoms together to form larger molecules. And it turns out that there is yet another conservation law. So we've talked about conservation of mass. We also have law of conservation of angular momentum. And this one's kind of nifty. What it boils down to is that as the atoms and molecules in our dust cloud start to stick together, they start spinning. And as they spin, they collide and stick to other objects in their path until what we ended up with was something that looked like a modern day solar system. Now, you've probably noticed that that nebular hypothesis only takes us so far. It only gets us to the point where stuff starts to be in orbit around other stuff. Thankfully, we have another hypothesis, the protoplanet hypothesis, which explains how the solar system continued to form from that point. And what that says is that we know that stars are born in nebulas, but not all of the material in a nebula gets incorporated into that star. Some of it's just too far away to get drawn in by gravity. And so About 10% of the matter in a given nebula is going to form into a disk around the early star that's forming in the middle. And it's not going to stay that way because when we have matter, we have forces. So, inside of that disk, as molecules start to collide with each other, friction is going to act on them as they brush up against each other, which is going to slow them down and change their movement. So within that disk, we start to see little whirlpools, little eddies forming. And gravity, of course, is going to act on those whirlpools, those eddies, pulling the particles in them closer to each other so that they form tighter and tighter balls, sweeping up everything that's in their path, because the bigger that collection of matter gets, the stronger the force of gravity it has. So it forms a tighter and tighter ball, sweeping anything up in its path. Conservation of angular momentum tells us that it'll start to spin and orbit around the star in the center, forming what we call a protoplanet, or a loose collection of matter that is one day going to become one of the planets in that solar system. And any uncollected material, anything that was just a little bit too far away to get incorporated into one of these protoplanets, is going to remain as space debris like asteroids and meteors. All right, as we continue to form our solar system, we're going to zoom in on planet Earth and how it develops. But first, some terminology. See, we have some specific criteria for what makes something a planet. And those criteria change as we learn more about our universe, which is why we once classified Pluto as a planet because we didn't know what else to call it. But now that we've discovered other Pluto-like objects, we have a different term for what Pluto is. So we no longer classify it as a planet. In order to be a planet in our solar system, there are 3 criteria. Number 1, if it's going to be called a planet, it has to be in orbit around the sun. So our moon does not qualify as a planet because it's in orbit around Earth, not around the sun. It has to have enough mass to assume a pretty close approximation of a spherical shape. It doesn't have to be a perfect sphere, but it's got to be close to spherical. And it has to have cleared its orbit of debris, meaning there's no major chunks of rock in its orbital path. So, as a point of interest, Pluto fails to meet the criteria for the planet on those last 2 counts. It doesn't have a round shape, and its orbit is not cleared of debris. Now, Earth was still in its formation stages at the point where we were talking about it just now, so it didn't yet meet the requirements for us to refer to it as a true planet, but it's about to. So, at this point, Earth is still clearing out its interstellar neighborhood, and it was still very much under bombardment from any chunks of rock that happened to be in its path, which it turns out is a good thing for us, because the early Earth was not exactly what you would call friendly to life. It was very rocky and dry, no ocean, no atmosphere. If you think back to what we talked about when we talked about what Mars is like, what its environment is like, sort of similar to that. Not a hospitable place for living things. But this changed because the early Earth was heating up. Part of the reason for this heating is those meteorites I just mentioned. Every time one of them hit the Earth, well, they were moving, which meant that they had a lot of kinetic energy. And the law of conservation of energy tells us that that energy doesn't just vanish when they collide with Earth's surface. Due to friction, which you get whenever any two things run into each other, that energy was released as heat energy. That, combined with the heat released as the material that made up the early Earth continued to compress due to gravity, and the heat given off as part of the decay of radioactive atoms, warmed the early Earth to a balmy 3,600 degrees Fahrenheit. You know, something that would feel pretty nice right about now, given that it's been cold for what seems like forever. Now, this is hot enough for something exciting to start happening. Iron has a melting point just under 3,000 degrees Fahrenheit. So, all of the iron that made up the early Earth at this point would have liquefied. And iron being one of the densest materials that makes up the early Earth, it started to sink towards the center of that sphere. As it sank, it would release other materials as they vaporized or melted due to the heat, depending on what materials we're talking about. And that's crucial because one of those materials was water, which would have vaporized, escaped as a gas, cooled, and fallen back to the surface of the early Earth. So now we have the presence of water, and that's critical. Now, those three processes that were causing the early Earth to heat up, they couldn't go on forever. Radioactive decay means that eventually there's a lot less radioactive material heating things up than what we started with. The Earth clears its orbit after a while, so there are fewer collisions to heat things up. And things can only compress so far before the repulsive force of electrons entering each other's space starts to outweigh the inward force of gravity, which means that we're putting less heat in, and that heat energy is going to be used up doing things like vaporizing water. So over time, Earth is going to start to cool down. And as it cools down, something incredible is going to start to happen, which is not to say that I don't find all of this incredibly cool, but this is particularly of note because of how much this particular thing has influenced and continues to influence the development of the Earth. See, different materials have different melting points. Something that you probably talked about as a middle schooler when you talked about phases of matter. So, different materials transition from liquid to solid at different temperatures, which means that different materials would have solidified at different times as the Earth cooled. The oldest crystals that we found put this cooling starting to happen about 4.4 billion years ago. And the fact that different materials had different densities and reached different points in that sphere as they melted and then cooled at different rates all meant that the Earth began to separate into layers. A solid outer crust surrounded a gooey molten center with a hard metallic, mostly iron core in the middle where the force of compression is so strong that it prevents that iron from melting. Essentially, the Earth is a chocolate-covered cherry. And at this point, the early Earth underwent a pretty major bombardment by space debris. Specifically, a planet-sized object collided with the early Earth at an angle and knocked a huge chunk of Earth material off into space. This chunk condensed and rounded out over the force of its own gravity at exactly the perfect distance where it was close enough to be caught by Earth's gravity, but far enough away to go into orbit instead of just being pulled back in and crashing back down to Earth. This, of course, is our moon. And we can tell that it happened this way because the material that makes up the moon is about the same age as the material that makes up the Earth, but the chemical composition is very different. We don't see the heavier elements that we tend to find towards the center of the Earth in our moon. In fact, the composition of the moon is almost identical to the composition of the Earth's crust and upper mantle. There's a video about this in your optional extensions for this week that show us replicating this in laboratory collisions. So if you're interested, check it out because it's really cool. So here's a visual that shows that beautiful chocolate covered cherry like nature of the Earth. So the outermost layer, the crust, that's solid. Inside of that, you have liquid layers of the mantle, and then a liquid part of the outer core, and a solid inner core where pressure is so strong that even though it's ridiculously hot, everything is kept solid because of that force of pressure. Take some time here. Check out that graphic as much as you need to understand what's going on, and then move on with the video. All right, we're getting closer to a livable Earth, but we're still not quite there yet. So at this point, after that collision that produced the moon, we're still pretty rocky, now with some oceans as cooling continues and water vapor condenses into liquid water. But the early Earth is missing a critical component that would allow life to develop: an atmosphere. Remember, again, we talked about Mars, and Mars has a very thin atmosphere, which means that Mars tends to experience some pretty wild temperature fluctuations. And a rocky, atmosphereless Earth would have had something pretty similar going on. And that's just not good for living things. Thankfully, this is where my chocolate covered cherry analogy breaks down, because the structure of the Earth isn't quite like the structure of candy. Specifically, there were two factors that made some changes happen to that early Earth. The crust isn't perfectly solid, and the liquid mantle inside is incredibly hot. The next time you go to make pasta or soup or whatever you like to make in your house that involves boiling something, watch what happens as the liquid heats up. This is especially obvious if you're cooking something that's got nice big chunks in it, like a pasta or a soup, where you can watch the movement of those chunks. You'll notice that over time, even if you don't stir what's in the pot, things are going to rise to the surface and then sink back to the bottom and repeat that process over and over again. This is called convection, and it happens whenever something is heating up in a way that it can move freely and it's sitting on top of its heat source. Like, for example, that mostly iron core of the Earth, which is still heating up the liquid mantle. As the liquid heats, it expands, making it less dense and causing it to float upward towards the parts of the mantle closer to the crust. And as that liquid mantle gets farther away from the core, it cools down, becomes more dense, and sinks back down closer to the core. This creates a circular pattern within the mantle, which we call a convection current. Combine this with the fact that Earth's crust wasn't and still isn't one single solid hunk of rock. It's broken up into pieces, which means that when the mantle moves, it can push those pieces and they can move and press up against each other. We call this idea plate tectonics, and it's the reason that, for example, California has a lot more earthquakes than Vermont does. So when those plates of crust move around, we get all kinds of fun stuff happening at their borders, like earthquakes and the formation of mountain ranges, and critically, for this stage of Earth's development, volcanoes. Lots of volcanoes. Early Earth was incredibly, ridiculously volcanically active. We are going to explore this idea of plate tectonics a lot more next week. So if it sounds like I'm glossing over it for now, it's because I am, but we're going to come back to it. So these volcanoes, when they erupted, they did all of the normal volcano stuff like spitting out lava and firing chunks of rock into the air and releasing huge clouds of gas and smoke. That last one, that's the important one. Because volcanoes, when they erupt, release tons of greenhouse gases. Now, I'm sure that you've heard that term before, but just to refresh your memory, a greenhouse gas is unique in its ability to trap heat. So, the atmosphere of the Earth at this stage would have been mostly made up of water vapor, carbon dioxide, and various sulfur compounds. All greenhouse gases, all very good at trapping heat near the Earth's surface, which means that the temperature, the surface temperature of the early Earth can begin to stabilize because it doesn't drop drastically overnight anymore. It still goes down, but not the several 100-degree shifts that we could have had before that. Now, you will notice that this early atmosphere was still very much not friendly to the kind of life we have today. Take a look at the composition of the modern atmosphere just for comparison. Clearly, we are not done yet. Just as a point of interest, I have never actually seen a Jurassic Park movie all the way through from beginning to end. I've seen all of the movies, and I've seen all of the movies to date, but in pieces. So that's your fun fact about Miss Smith for the week. But I feel that I needed to make this joke anyways. So most of what happens from here on out in the formation of the Earth is the proper purview of living systems. So I'm not going to get into the major details, but essentially, now that we have an atmosphere and now that Earth's temperature has stabilized, the early oceans become a really ideal incubator for molecules to come together to form the first living things. The exact mechanisms for how this happened, well, we have a lot of ideas, but it's very much still an area of hot debate. But however it happened. Life arrived. And those individuals that were best able to survive in the environment of the early Earth had the greatest chance to reproduce and make more living things. A major game changer here was that somewhere along the line, one of these early organisms developed a technique for turning sunlight into sugar called photosynthesis. A byproduct of this process is the production of a whole heck of a lot of oxygen. So this finally enables life to expand and flourish. I'm going to leave this graphic up for just a little bit because it really nicely illustrates how we got from where we started in this lesson to an Earth that looks like our modern Earth. You will notice as you go about your work this week that I left things pretty light on the assignment front. This is because I was kind of figuring that some of you might need a little more time on your choice projects. So if you're not quite happy with how it shook out, or you didn't finish and you want to, you have the opportunity to do that this week. And if you're someone who got it done and is satisfied with the work that you did, you've got a little bit of a break this week. Make sure that you're solid on the concepts that we've been over in this lesson and be ready to do some work with them next week. Be good, be safe, be kind. Don't do anything I wouldn't do. Wash your hands and go do good work.